Welcome to Iron Process, a journey into some of the most remarkable industrial manufacturing systems in the modern world. From giant suspension bridges and offshore drilling platforms to towering cranes and massive skyscrapers, many of humanity's greatest engineering achievements rely on steel wire ropes for strength and structural stability. Designed to carry enormous loads while operating continuously for decades, these giant steel cables are the result of an extremely precise and highly engineered manufacturing process. Steel wire rope is one of the most important load-bearing components used in modern engineering. Structurally, it is not a single solid steel bar, but a multi-layered system made from numerous high-strength steel wires twisted together into strands, which are then wrapped around a central core to create the finished rope structure. This specialized design allows the rope to achieve both extremely high tensile strength and the flexibility required for demanding industrial operations. To obtain these mechanical properties, steel wire rope must pass through a long and carefully controlled manufacturing process involving raw steel preparation, wire drawing, heat treatment, stranding, rope laying, and extensive quality inspection. Every stage of production directly affects the final rope's strength, durability, fatigue resistance, and operational lifespan. Steel wire rope technology first emerged in Germany in 1834, closely associated with engineer Wilhelm Albert, who developed one of the earliest wire rope systems for use in mining operations. His invention solved many of the limitations of natural fiber ropes, which struggled under heavy loads and deteriorated rapidly in humid underground environments. From its early use in mining industries, steel wire rope quickly proved its advantages due to its high tensile strength and long-term durability under extreme working conditions. By the 20th century, steel wire ropes had become essential components in suspension bridges, lifting systems, elevators, offshore drilling rigs, industrial cranes, and many other large-scale engineering structures. Every steel wire rope begins with a raw material known as wire rod. This hot-rolled steel product is manufactured into long round bars before being coiled into large rings for transportation and storage. The diameter of the original wire rod is significantly larger than the finished steel wires used inside the completed rope structure. Because of this size difference, the material must undergo a long sequence of mechanical and metallurgical transformations before it can become fine, high-strength steel wire suitable for rope manufacturing. The quality of the incoming steel material is critical throughout the entire production chain. From this raw wire rod, manufacturers produce individual steel wires, which are later assembled into strands and finally combined into complete steel wire ropes. As a result, the quality of the raw material directly affects every later stage of manufacturing. In industrial conditions, the surface of wire rod is never perfectly clean. During hot rolling and storage, the steel surface becomes covered with mill scale, rust, oxidation layers, and various contaminants. If the material entered the wire drawing process in this condition, friction between the steel and the drawing dies would increase dramatically, leading to unstable drawing conditions, accelerated die wear, and surface defects on the finished wire. Even relatively small imperfections can reduce fatigue, resistance, and mechanical strength during long-term operation. Because of this, the wire rod first passes through an inspection and preparation stage before entering the drawing process. During this operation, manufacturers inspect incoming material, remove defective sections, classify the steel according to specifications, and prepare the feedstock for stable processing throughout later manufacturing stages. Before drawing begins, the steel surface must also undergo a complete cleaning process. This stage removes rust, oxide scale, and surface contaminants while preparing the material for stable drawing operations. The objective is to create a smooth and uniform surface capable of minimizing friction during deformation, while also allowing lubrication compounds to bond effectively to the steel surface. In industrial manufacturing systems, surface cleaning is generally performed using two primary methods. The first is chemical pickling, where the wire rod is treated using acid-based solutions designed to dissolve oxide scale from the steel surface. This process provides relatively uniform cleaning results and is especially suitable for continuously coiled wire rod materials processed in large-scale production systems. Once the surface has been cleaned, manufacturers usually apply phosphate coatings together with lubricating compounds or intermediate treatment layers. These coatings form a protective interface between the steel wire and the drawing dies, greatly reducing friction throughout the drawing process. The second cleaning method is mechanical descaling. In this process, oxide layers are removed using mechanical brushes, scale-breaking rollers, or steel shot blasting systems. Mechanical descaling is particularly effective when rust and oxidation layers adhere strongly to the steel surface. Once the wire rod has been completely cleaned and prepared, the material finally enters one of the most important stages in the entire manufacturing process: wire drawing. During wire drawing, the original steel rod is gradually transformed into fine, high-strength steel wire suitable for rope production. This process works by pulling the steel through a sequence of hardened dies containing progressively smaller openings. As the wire passes through each die under tensile force, its cross-sectional area decreases, while the material simultaneously elongates. Through repeated controlled deformation, the steel gradually reaches the dimensions required to produce fine industrial wire filaments. As the diameter decreases, the internal structure of the metal begins experiencing cold work hardening. Tensile strength increases significantly, while ductility gradually decreases. Because of these changing mechanical properties, the wire cannot be reduced from large diameter to final size in a single operation. Instead, manufacturers perform multiple sequential drawing stages, with each pass reducing the wire diameter only by a carefully controlled amount. This gradual reduction minimizes the risk of wire breakage while helping manufacturers maintain tighter control over surface quality, dimensional accuracy, and mechanical performance. Through repeated drawing operations, the original wire rod is slowly transformed into fine, high-strength steel wire capable of carrying enormous industrial loads. However, continuous cold deformation progressively hardens the material and reduces formability. To restore workability during production, manufacturers introduce intermediate heat treatment stages between drawing operations. One of the most important intermediate heat treatment processes used during steel wire production is known as patting. After several drawing passes, the wire becomes increasingly hard and brittle due to cold work hardening. If additional reduction continued without treatment, the possibility of wire failure would increase dramatically. To prevent this, the wire passes through a heat treatment furnace before being cooled under carefully controlled conditions and returned to the next drawing stage. This operation partially restores the internal microstructure of the steel and allows further deformation without excessive material failure. Once the wire reaches the required diameter, manufacturers often apply a galvanizing layer to improve corrosion resistance. During galvanizing, a protective zinc coating is added to the steel surface. This zinc layer protects the finished wire from moisture, corrosion, and environmental exposure, especially when the completed ropes are intended for offshore engineering, marine environments, humid climates, or long-term outdoor operations. After drawing and heat treatment are completed, the individual steel wires move into the strand formation stage. During this process, multiple wires are gathered together and twisted into a predetermined configuration to form a strand. one of the main structural elements inside the completed steel wire rope. Throughout the stranding process, manufacturers carefully control important technical parameters, including wire count, lay direction, lay length, and strand geometry. In most configurations, the outer wires are twisted around a central wire to create a structure that remains both stable and flexible during operation. The strand directly influences the rope's tensile strength, bending performance, fatigue resistance, and operational lifespan. Because of this, the entire stranding operation must be tightly controlled to ensure even wire distribution and stable performance under load. Alongside strand production, manufacturers also produce the rope core. Positioned at the center of the rope structure, the core acts as the axis around which all strands are wrapped during rope closing. Although hidden inside the completed cable, the rope core plays an essential role in maintaining geometry, structural stability, and load distribution. The core helps preserve the rope's round shape, while supporting equal load transfer between surrounding strands. Depending on technical requirements, the core may be manufactured from either steel or fiber materials. Steel cores are generally used in applications requiring greater load capacity and structural rigidity, while fiber cores provide increased flexibility and improved vibration absorption. After the core has been prepared, the strands move into the rope laying stage, where they are wrapped around the central core to create the finished steel wire rope. During rope closing, specialized industrial machines combine rotational movement with forward motion to produce the final helical rope structure. Throughout this operation, manufacturers must carefully control important technical parameters, including lay length, lay direction, strand positioning, and strand tension. Depending on rope design, the strands may be arranged in one or multiple concentric layers around the core. Maintaining equal tension between all strands is extremely important. Uniform tension helps preserve the rope's geometry, reduces structural deviation, and ensures stable load distribution during operation. Once the rope structure has been fully formed, the cable undergoes inspection to verify geometry, concentricity, and structural stability before identification marking begins. This inspection process helps engineers detect irregularities in strand alignment, lay configuration, or tension distribution that may have developed during rope closing. The rope is then marked along its length using paint markings or technical identification codes. These markings help distinguish specifications while supporting traceability during transportation, installation, maintenance, and operational service. Following identification marking, the rope surface is lubricated and coated using protective grease or anti-corrosion compounds. This lubrication layer reduces internal friction between wires, limits moisture penetration, and significantly extends the operational lifespan of the rope. Combined with the galvanized zinc coating already present on each steel wire, this lubrication system creates a multi-layer protective barrier for the entire cable structure. For extremely large steel wire ropes with massive diameters and exceptional lengths, conventional production systems are no longer sufficient. In these situations, manufacturers use linear track-based production systems, where the rope closing machine moves continuously along rails while performing the rope laying operation. During production, the central core and surrounding strands are continuously fed into the moving machine. As the closing system advances along the track, the The strands are wrapped around the core to produce extremely long cables required for suspension bridges, offshore engineering systems, and other heavy-load industrial structures. Once manufacturing is complete, the finished rope must undergo extensive quality inspection before leaving the factory. This stage confirms that the rope satisfies technical specifications and can safely operate under real engineering conditions. To evaluate braking strength, manufacturers cut a sample section from the rope and install it inside a hydraulic tensile testing machine. The sample undergoes a braking load test to determine actual maximum tensile strength before the results are compared against technical standards and design specifications. In addition to tensile testing, manufacturers also perform non-destructive testing using ultrasonic and magnetic inspection systems. These inspection methods allow engineers to detect hidden internal defects, including cracks, structural irregularities, and internal damage that cannot be identified visually. After successfully passing all inspection procedures, the rope receives certification confirming compliance with industrial quality and technical standards. Production then moves into end termination, most commonly involving the formation of a rope eye. This loop termination allows the finished rope to connect directly to crane hooks, lifting systems, anchoring points, and structural support equipment. The rope eye is typically formed by bending the cable into a loop and securing it using metal sleeves through swaging operations, or by splicing the strands directly back into the rope structure. The specific method depends on working load requirements and technical operating conditions. Because the termination transfers load directly from the rope into connected structures or equipment, this component must be manufactured with extremely high precision and mechanical strength. Once the termination process is complete, the rope becomes a fully functional industrial load-bearing component ready for transportation and installation. After inspection and end termination are completed, the rope enters the final preparation stage for transportation and delivery. Since some industrial wire ropes can reach hundreds of meters in length and weigh enormous amounts, careful handling procedures are required to prevent deformation, impact damage, and surface contamination. In most cases, the completed rope is wound onto large cable drums or reels, matched to the rope's total length and diameter. During these handling operations, factories use forklifts, hoists, and industrial cranes to safely transport the heavy cable coils. Once wound and secured, the rope is protected using external coverings and fixed firmly onto transport vehicles to minimize environmental exposure and mechanical damage during shipping. Depending on the destination project, steel wire ropes may be transported using specialized trucks, rail systems, or marine transport vessels. For offshore engineering projects, the ropes are typically delivered through industrial ports before being transferred onto installation ships operating at sea. After arriving at the construction site, the ropes are delivered together with technical documentation and certification records before entering installation and operational service. Once manufacturing, inspection, and transportation are complete, steel wire ropes begin operation across a wide range of engineering industries. In offshore engineering and oil and gas operations, they are used to moor drilling platforms, stabilize marine structures, and support heavy industrial systems operating in deep water environments. In construction and structural engineering, steel wire ropes are widely used in suspension bridges, cable-stayed bridges, crane systems, lifting equipment, and tensile support structures. Their combination of strength, flexibility, and durability makes them essential components in modern infrastructure systems. In heavy industrial lifting operations, steel wire ropes are also used in shipbuilding, oversized cargo transportation, steel structure assembly, elevators, industrial cranes, cable transport systems, and material handling equipment. Depending on operational requirements, manufacturers engineer wire ropes with different levels of flexibility, abrasion resistance, fatigue performance, and tensile strength. Because of these characteristics, steel wire rope has become one of the most important structural components used throughout modern engineering systems, especially in applications requiring high load capacity, operational reliability, and long service life. From raw steel material to finished cable, the production of steel wire rope represents far more than a simple twisting process. It is a highly controlled industrial manufacturing system, combining metallurgy, materials, science, precision engineering, heat treatment technology, and advanced mechanical production. Beginning with hot-rolled wire rod, the material passes through surface cleaning, multi-stage drawing, intermediate heat treatment, galvanizing, strand formation, rope closing, lubrication, inspection, and final testing before becoming a finished engineering component. Even after manufacturing is complete, every rope must undergo rigorous technical inspection to verify compliance with strict industrial standards before entering real-world service. Through the integration of advanced manufacturing systems, metallurgical engineering, and precision process control, modern steel wire ropes are capable of achieving extremely high tensile strength while still maintaining the flexibility required for practical industrial operation. These mechanical properties make steel wire rope one of the most important load-bearing elements used throughout modern engineering systems, from suspension bridges and offshore drilling platforms to industrial lifting equipment and heavy transport systems. Although rarely visible within completed structures, these giant steel cables function much like structural tendons supporting many of humanity's largest engineering achievements. The evolution of steel wire rope manufacturing also reflects the broader development of modern heavy industry itself. As infrastructure systems continue increasing in size, complexity, and load demand, manufacturing technologies continue advancing to improve durability, precision, safety, and long-term operational reliability. Behind many of the world's largest engineering systems are industrial manufacturing processes, operating with extraordinary levels of control and accuracy. Steel wire rope remains one of the clearest examples of how engineering, materials, science, and large-scale industrial production combine to create components capable of carrying enormous loads continuously for decades. Thank you for watching until the end of this story. If you enjoy content like this, don't forget to like, share, and subscribe so you won't miss our upcoming explorations. Iron Process, thanks you for watching, and we'll see you in the next story.